So to kind of help you out with doing oxidation states, let's take a look at about 4 simple examples for figuring out oxidation states. So we'll take a look at SO2, OF2, Na2, CO3, sodium carbonate, and V, NO3, 5. So with all of these, there's 2 rules we're going to consistently apply. First, the sum of the charges has to equal the overall charge of the molecule. Second, we want to apply the rule that more electronegative element takes a negative charge. So for SO2, we've got our rule, sum of the charges has to equal the overall charge. In this case, our overall charge is 0. Now we don't have any more rules to guide us other than oxygen's more electronegative than sulfur, so it's probably going to take on the negative charge. So oxygen, taking on negative charge, takes 2 electrons to get it to the neon configuration. So we're going to guess a -2 charge on oxygen. This tells us the charge on sulfur plus twice the charge on oxygen should give us 0. So this will give us sulfur in a +4 and oxygen in -2. How about OF2? Charge on oxygen plus twice the charge on fluorine has to equal 0. Now fluorine, we have a rule for this. Fluorine has to be -1 if it's in any compound. So we're going to put a -1 charge for fluorine. This tells us then that the charge on oxygen plus twice the charge of fluorine should give us 0. So in this case, oxygen is going to be a +2. Now we have the guideline that oxygen is generally -2. Well, that's true if and only if it's the more electronegative element. If it's ever in a situation where it's competing with a more electronegative element, in this case fluorine, or it's in a competition with itself, those will be the times we don't see anything other than a -2 oxidation state. How about Na2CO3? Well, there's 2 approaches we can take with this. We still have the overall charge has to equal the sum of the individual charges. So twice the charge on sodium plus the charge on carbon plus 3 times the charge on oxygen has to give us 0. And sodium being column 1 element, we can make the guess that it's probably +1. And oxygen, being the most electronegative element in this compound, is probably -2. So we get twice the charge on sodium plus the charge on carbon plus 3 times the charge on oxygen should give us 0. So this will give us a charge of +1 on sodium, +4 on carbon, and -2 on oxygen. But this can kind of be an unsettling conclusion because we had to make 2 guesses here to figure out the unknown carbon oxidation state. So if you know your polyatomic ions, there's another way you can solve this. Carbonate, CO3, has a -2 charge. So that tells us that the 2 sodium atoms had to compensate for that -2 charge, and they'll do it by each taking a +1 charge. So if each sodium is a +1, there's 2 of them, that's +2. That'll cancel out the +2 in carbonate. So we have the charge on carbon plus 3 times the charge on the oxygen now equals -2. Our rule is oxygen is more electronegative. It's going to take the negative charge. In this case, again, it's going to take a -2 charge to fill up its octet. So this will give us carbon plus 3 times the charge on oxygen gives us -2. So we'll end up with a +4 charge on carbon and a -2 charge on oxygen. What about vanadium 5 nitrate? Well, if you don't know your polyatomic ions, you're completely out of luck on this. We have no guidelines when it comes to transition metals. So what you have to do is recognize that nitrate is the NO3 -1 anion. We've got 5 of them down here, which means vanadium has to take a +5 charge to compensate for those 5 negatively charged nitrate ions. We've also got charge on nitrogen plus 3 times the charge on oxygen has to give us -1. And once again, oxygen is the more electronegative element, so it's going to take the negative charge, in this case, a guess of -2. So we guess -2. This gives us nitrogen plus 3 times the charge on oxygen is -1. And we solve this, we get the charge on nitrogen is also +5, and the charge on oxygen is -2.